Okay, we're working, we're on, we're hot. Okay, let's look at these words and see if not only can we define the words, but we can make connections among the words. Okay, let's start with a number one. Okay? One, compressibility. What is compressibility? What does it mean? And where is my compressibility people? Yes, Mohammed, what do you got for us?
It's when the density changes, both the pressure and the temperature will change, generally.
Generally, so when you compress a gas, obviously we're talking about gases, correct? So when you compress a gas, what are you doing?
You're changing both the temperature and the...
Why are you changing the temperature? Because compressibility requires what? Starts with a P. Pressure, good. So higher pressure, higher... Whose law is that? Whose law relates pressure and temperature? Gay-Lussac, right? And because gas and pressure are what? What's the relationship between, pressure and temperature?
Because the higher the pressure, the higher the temperature.
But what's it called? It starts with a P or a D. Direct or proportional, correct? Masi, you get it? Okay. So now, when I compress a gas, I'm going to change its temperature. Yes?
Yes.
But I can change its temperature. I can change its volume, correct? Yes? If it was constant volume, what would definitely change? Temperature. It was constant temperature, what would definitely change? Volume. But couldn't both change? They couldn't? Of course, it's called combined gas laws, absolutely. Okay? So, and then if I compress it, we have Gay-Lussac's law there. We have the words proportionality there. We have density. Is density changing? What's density? What is density?
Thickness of an object or a gas.
Would you say thickness of an object? Thickness. I like that. How is it thick? Is the air thick today? It's thick. Is it dense? Yeah. Thick steak. Do you ever have a thick steak? Thick. Real thick. As opposed to chicken, which is kind of like da 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 da. I want a thick steak. Thick. Dense, right? Okay. So density. I use rho. Yeah? Density equals mass over volume. What's the density of hydrogen at STP? What's the density of hydrogen at STP? If I take a sample of hydrogen, and I know that it's at STP, what would the density of it be? Simon?
0.089 grams per liter.
Say that again?
0.089
0.089 grams per liter? Is that right? Is that what you said?
Yes, that's what I said.
Excellent, I like that. He had it right at the tip of his tongue. That's really weird. How did you know that?
I told you.
And how did you know?
I calculated it.
You calculated it?
1 mole of any gas occupies 22.4 liters.
1 mole of any gas occupies 22.4 liters at STP, and then what'd you do?
And 1 mole of H2 is
2 grams.
Yeah.
Wow, you knew that. You did all that.
Density is equal to mass divided by volume.
God bless all Ethiopians. I love it. So 2 grams over 22.4 liters. And what does that equal? Somebody else do it. We'll do a verification of their calculation.
No verification needed.
No, no verification needed. Excellent. I like that. But you know, my father said when I was a kid, he says, only fools are positive. I like that. I'm not sure why he used to say that. Maybe he was wrong a lot. I don't know. 2 divided by 22.4, what do we got?
Yes, it checks out.
It checks out, so 0.089? Is that what you said? 0.89 grams per liter. Yes? I like that a lot. I like that. Pretty cool, actually. I like that. I like that a lot. So if I compress the gas, I'm going to do what? If I compress the gas, I'm going to do what?
Increase the density.
I'm going to increase the density. Exactly. Okay. So are we done with compressibility? Are we cool? Okay. So we've looked at, with compressibility, we've done gas density. What else? Gay-Lussac's law. Where's Gay-Lussac? Gay-Lussac's law. Anything else? We said about the combined gas law. We talked about pressure volume changes. We talked about pressure temperature, Gay-Lussac combined. All right, cool. Excellent. Excellent. So now what's next? What's number 2? Diffusion. What's diffusion? What is that, diffusion? Mark.
The movement of a fluid from an area of high concentration to an area of low concentration.
The movement of a fluid from an area of high concentration to an area of low concentration. So here I have high, here I have low. So it's going to go from low to high, is that correct? High to low. Excellent. I like that. Try to get you. Now, that's right. That's right. And that's also how energy travels. A lot of things go high to low. Energy as well. Yes? Energy goes high to low. Is there something maybe in there, some connection between gases going high to low and energy going high to low? A point to ponder. A point to ponder. It's actually I think it's the second law of thermodynamics. That energy doesn't travel uphill, it travels downhill. Not really, I'm just making a comparison. It goes from high to low. You ever see water by itself, the stream go up the mountain? Would that be a little weird? Yeah. So a fluid. Now, why didn't you say gas? Is gas a fluid?
Yes.
It's not?
Yes.
Gas is a fluid. Gas is a fluid. Gas is a fluid, yes. So you can say that. You can say a fluid. Water, liquid, gas, high to low concentration. Now, let's just jump a little bit, just for a moment. What word closely relates, I'm going to put different geometric figures on here. What word closely relates to diffusion of gases? It starts with an E.
Diffusion.
Effusion. What's effusion? Who's my effusion person? Excuse me, my throat is very... It's actually growing hair. I have to get in there and tweeze out the hair because I have giant hair growing in my throat. The coffee helps to get rid of it. I have a hairy throat. It's a little weird. But anyway, yes?
So effusion is the process in which a gas escapes through a small hole, and the diameter of that hole is vaguely defined as being a lot smaller than the free path of molecules.
All right, wait a second, hold it. We gotta say this again. You're giving me far more information than I wanted at this time, but I'm going to take it. Okay, now. Effusion is when gas travels through a little opening, an aperture. Can we call it an aperture? Okay, it goes through an aperture as opposed to the perfume. Anybody got any perfume with them?
No, not today.
Not today? Okay. No perfume? I just wanted one snot, one. Jen, do you have any perfume? I know. I just want just a little bit. I'm not going to use all. Oh, we got that. This is such a cute thing. All right, this is it. You ready? Quiet. Now smell the air around you. Okay. Okay? Thank you. You're a wonderful person. I don't care what your mother says. Excellent. She's wonderful. Okay. Now, so what's the diffusion we know is molecules traveling without borders. You have Doctors Without Borders. Well, gas molecules traveling without borders is kind of diffusion, right? Effusion is when it goes through like a little hole. We call it an aperture hole, right? Now, Maunus is going to define for us, he's going to feed me the information, he's going to define for us, like, did you ever wonder, well, what's the size of the hole? Maunus.
Okay, so the size of the hole, like the diameter,
The size or the diameter of the hole
is vaguely defined.
is vaguely defined,
As being considerably smaller.
is defined as being considerably smaller than
The free path of molecule.
the free path
Of the molecule.
of the molecule.
And the free path of molecules is defined as the average. Is defined as the average distance molecules travel between each collision.
So the average distance molecules travel between collisions. All right, I got this. So you know that molecules collide, right? Right. So it's traveling through a hole, right? This is a small board, right? Really tiny hole, right? But we're going to blow the hole up. So we're going to blow the board up, the hole, right? It's going to be like this big. Okay, we're going to blow it up. Yeah, can you imagine that? We're going to look at it like with a microscope. And the piece of paper is like this wide, or whatever it is. Let's say it's through a piece of paper. It's effusing through a piece of paper and a hole in the paper. Okay, is that okay? All right. So the piece of paper is really thin, but we're going to blow the paper up so it looks like this. And here's the hole. My finger is the path of the hole through the paper, right? Now we know that molecules collide with each other, correct? Now, the average distance between collisions, or the average space a molecule has, is going to be
In the diameter.
is going to be the approximate diameter of the hole. So if a hydrogen molecule keeps banging into other hydrogen molecules like this, and let's say every time between collisions it's like an inch or a centimeter, let's say. Between collisions. Let's say it's a centimeter. It's obviously smaller than a centimeter. Then the hole will be a centimeter. Do you get that? So the average distance a molecule goes between collisions, is that good? The average distance a molecule goes between collisions is actually the size of the opening, the hole, in which gas effuses. Where's effusion?
This side.
Here. Right? Yes? Are we cool? So in order to talk about diffusion, you have to kind of talk. Anybody smell the perfume yet?
Yes.
You smell it? Okay. Now remember, I sprayed it that way, and they already smell the perfume over there. Now, what is the average speed of, let's say, your average molecule of gas? Somebody look that up. Average speed of put that in your Google search. Average speed of the average molecule of a gas. Okay. Now, let's do number 3. Number 3 says Charles' Law. Charles' Law. Has anybody looked up Charles' Law? Do we have any talk about Chuck laws? Chuck's Law? Charles' Law? Carlos in Spain? Yes.
As the temperature of a gas increases,
As the temperature of a gas increases,
the
the volume will increase proportionally. Excellent. Did anybody look up any information on Charles, Professor Charles? What was Charles' last name? Charles. Yeah. Okay. Did anybody look anything up on him? No? Ooh. Yes, you did? What do you got, girls? Excellent. We have some. Simon, you didn't look up anything on Charles.
It says Charles' Law.
I know, but it's okay. But you want to get to know the man behind the law, okay? Ava, what do you got, girl? Ava's from Greece. She's
Oh, sorry.
wonderful.
Sorry.
What are you sorry about?
We don't have to.
She doesn't have Charles. She got confused. That's okay. Yes.
It says you have like 20% battery left.
I have 20% battery left. Okay, thank you. Thank you, Mr. Eveready. Excellent.
He was born in 1746.
Charles was born in 1746. Where was he born?
Yeah, France.
He was born in France. I'll give you, this is a great piece of information. Who actually gave him credit? Strangely, Charles died without publishing a lot of his work. Which scientist actually published his work and gave him a lot of credit? Now, in some locales in the science community, Charles' law is actually called Gay-Lussac's law, volume and temperature. But who was behind actually giving credit to Charles for Charles' law? He's a really nice guy. A lot of Charles's work was published posthumously. What does posthumously mean?
After death.
After death. Excellent. So, who did it? Yes?
Joseph Louis Lusac.
Gay-Lussac. Gay-Lussac. Charles Louis Gay-Lussac. Is that his first name? Charles Louis? Joseph Louis. Joseph Louis Gay-Lussac. That's who actually ended up publishing a lot of Charles' law. Pretty cool, huh? Is that cool or what? Yes? Yes, pretty cool. Okay, so what do we got here? So now we have Charles' law. Okay. We have anything else on Charles? I got to charge my battery, so I'm going to have to bring my computer up here to charge it. So I want to do, what is this? Gas review part 1. Is that okay? Yes? Yes, one more thing. Yes, about Charles.
Yeah, Charles and the Robert brothers launched the world's first hydrogen filled oven.
Yeah, Charles and what brothers?
Robert brothers.
I can't hear you.
Robert.
Robert?
Yeah.
His brother Robert?
No, Robert brothers.
The Robert brothers?
Yeah.
All right, we're going to kind of forget about that for a minute. We'll go back on that because I'm not sure I understand your pronunciation. Happens sometimes in international schools, but that's okay. It's my ears, not his speech. Okay, so we're going to call this part 1, gas review, okay? And then I'll dump this in, make a video, and then we'll come back and do part 2. You'll never know I was gone.